Uh, Hello. Today I will tell you something about detecting obstacles within the driving lane and vehicle speed adjustment algorithm. So this presentation will be in 4 parts. Firstly, I will introduce you with the topic. Secondly, I will describe the proposed algorithm. Then I will present algorithm testing and evaluation. And finally, I will conclude the paper with short conclusion. So advanced driver assistance systems are electronic systems that are commonly used in modern vehicles, and they are used to assist drivers in driving and parking to increase the safety. So part of this paper is working on part of driving line detection and collision avoidance systems that are also very common. They use mostly camera, but they can also use radar or lidar as input. So 2 key areas of research can be identified for this approach. First is using computer vision and image processing, while another is using deep neural networks. We will use the first approach. To implement that algorithms, we will use OpenCV library in a C++ programming language. For the evaluation, we used open source simulator Carla, and finally we used robotic operating system to perform braking. First step of the algorithm is to retrieve the video frame and to convert that video frame into a format that can be processed by using OpenCV library. Retrieving and formatting was done inside of Carla simulator by using a ROS development framework. Here you can see a picture of example of video frame captured by RGB camera in front of the vehicle. Next step is video frame pre-processing, where first sub-step is inverse perspective mapping. In this sub-step, we define 4 points which will used as points that will border the perspective mapped picture, where we will get a so-called bird's eye perspective, and we will reduce number of background noise. Also, we used a Gaussian filter to reduce amount of detail by blurring the image. Then we transport RGB video frame into HSV color model to provide robustness to illumination changes when filtering. Then we used color filtering, and then we applied Canny edge detection output. You can see here that the output is a binary image where pavement markings edges are seen as white pixels. And then we used random sample consensus iterative method that enables parameter estimation of some mathematical model to eliminate outlier values. We used straight line to define to detect pavement markings, and we ran 250 iteration twice for each of the pavement marking, and as output we got a set of points that describe the line model best. They have the most inlier values. So when we have pavement markings, then we have our driving lane area, because it is bounded by these pavement markings. And then we transform that binary image to the original perspective, and we apply a Canny detector on input video frame original, so that we get edges of the obstacle and pavement markings inside of driving lane area only. Next step is to classify some obstacle that is in front of our vehicle. A second. So we used 2 obstacles that were present in simulator. One is vehicle, second is pedestrian. And to perform detection and classification, we measured the ratio of number of pixels that are representing the obstacle edges on some y-axis value, on some row on the image, to the width of the lane on that y-axis value on the image. So when we have a vehicle, it will occupy a larger area in front of our vehicle in driving lane. So we divided that area into two parts. First is closer to our vehicle and when the obstacle is larger. So we used a smaller threshold for the ratio I mentioned in first point. And in further distances from the obstacle, we increased that threshold. So we assume that this threshold will be used to detect vehicle because vehicle does pass this threshold while a pedestrian is smaller and it shouldn't be detected. So to be sure, we search inside of a video frame if there are 5 or more rows where these thresholds are exceeded, and then we conclude that this obstacle is vehicle, other vehicle, if that threshold is exceeded. So to estimate distance, we defined several values. So here you can see red, marked as red, is a lane width at some coordinate. Also, green is image row that contains the most pixels, which is used to detect vehicle as an obstacle. And also we have the maximum y-axis value of some obstacle on the image. In order to estimate distance, we define 2 models. First model, you can see on the left side, it is the functional relationship of the distance from the vehicle and the maximum position of the pixels that belong to the obstacle on the y-axis. That would be the green one, the green line. After that, we defined the functional relationship of the stopping distance from the vehicle speed. That's some initial speed, which was a vehicle driving, and when we detected some obstacles, so we applied maximum braking force. That was empirically determined in Carla simulator by using Audi e-tron model. So you can see that both of the models are not quite linear. So when we use that models to find estimation distance of the obstacle. So we noticed that visibility is around 80 meters. So we divided that region to 2 parts, first 40 meters and second 40 meters. And then we tried to find the position of the row on the y-axis to find where the obstacle first time appears. And then we use the model from the last slide to estimate distance. So we use different techniques depending on area and about obstacle. When we have a vehicle, then we just search for the highest value on the y-axis where the ratio of the pixel to the bandwidth of the driving lane is higher than 0.2, and then we apply model to find a distance. When we have a car which is further from us, then we will just search for a maximum value on epsilon axis, y-axis. When we have pedestrian, after Canny edge detection, it will be smaller. So we will try to find few rows that contain 4 pixels that represent pedestrian limbs. And when it is further from us, from 40 to 80 meters, we find 2 pixels that are representing limbs. So when we when we estimate the distance, then we use ROS to apply maximum braking option, which was only available in simulator. So to test the algorithm, we used two steps of evaluation. So first, we collected image data set from Carla simulator using a built-in RGB camera, where we used 76 pictures for the vehicle as an obstacle and also when pedestrian is an obstacle. Each picture contains different distance from the obstacle. So when we examined classification, so only in over 6 of the cases it was wrongly classified as a pedestrian, and when pedestrian was misclassified as a vehicle or not detected, it happened in around 5% of the cases. So you can see also that mean absolute error of the distance estimation is higher when we have a pedestrian, because it is polar and it is harder to detect him. So here you can see output picture when with detected pavement markings and classification and estimation to the distance. So left we have a vehicle as a obstacle, and right we have a pedestrian, and this is just showing on the RGB video frame. Second approach was to create a simple simulations in a real time where a vehicle was moving in the middle of the lane along the roadway marked longitudinal pavement markings at the dry road at the daytime. So we used a different speeds with 10 kilometers increments. And you can see in the tables that only at the lowest speed, our vehicle has stopped and at the expected measured distance. And while we have the greater speed, then there is some deviation. And finally, when we reach to the higher speeds, then we have a collision with an obstacle. Also, as expected, this error is higher when we have a pedestrian as an obstacle than when we have just a vehicle. So finally, we can see that this appliance of computer vision can be used to detect line, and in combination with ROS, we can change the speed of the vehicle. But this algorithm has proven to be reliable when we have some data set of images where we test estimation and classification, while when it is tested in a real-time scenarios, then we have a problem because there is deviation from the desired stopping distance. And when we have a higher speeds, then we have a collision with the obstacle. So because of that, we need further refinement of the algorithms to make this algorithm applicable in a real time. So that will be it from my presentation. If you have some questions, please ask.
Okay, thank you for the interesting presentation, Mr. Srđan. Okay, any questions or comments?
Usually, what is the range of errors for detecting obstacles in driving lanes?
So in this case, we had the actual, there was some small violation when we have higher distances where same pixel represent different meters. So in that cases, we will have a few meters mistake, okay. But there are situations when we misclassified the obstacle, and in that case, it could be a higher mistake, but that should be repaired in next video frame. So it should be fixed.
Around few meters.
Few meters, but I say when it is wrongly classified, then wrong estimation technique is used. So it could be 10 or maybe even 20 meters.